Hello dear students, we are going to discuss today on flow of heat part 4. Heat exchangers or interchangers are devices that facilitate the exchange of heat between two fluids that are at different temperatures while keeping them away from mixing with each other. A heat exchanger is a device that is used to transfer thermal energy called enthalpy between two or more fluids, between a solid surface and a fluid, or between solid particulates and a fluid at different temperatures and in thermal contact. In heat exchangers, there are usually no external heat and work interactions. Heat exchangers are commonly used in practice in a wide range of applications, from heating and air conditioning systems in the household to chemical processing and power productions in large plants. They differ from mixing chambers in that they do not allow the two fluids involved to mix. In a car radiator, for example, heat is transferred from hot water flowing through the radiator tubes to the air flowing through the closely spaced thin plates outside attached to the tubes. In most heat exchangers, heat transfer between fluids take place through a separating wall or into and out of a wall in a transient manner. In many heat exchangers, the fluids are separated by a heat transfer surface, and ideally they do not mix or leak. Such exchangers are referred to as direct transfer type or simply recalibrators. In contrast, exchangers in which there is intermittent heat exchange between the hot and the cold fluids by thermal energy storage and release through the exchanger surface or matrix are referred to as indirect transfer type or simply regenerators. Such exchangers usually have fluid leakage from one fluid stream to the other due to pressure differences and matrix rotation, valve switching, etc. Common examples of heat exchangers are shell and tube exchangers, automobile radiators, condensers, evaporators, air heaters and cooling towers. If no phase change occurs in any of the fluids in the exchanger, it is sometimes referred to as a sensible heat exchanger. Heat transfer in the separating wall of a recaliberator generally takes place by conduction. However, in a heat pipe heat exchanger, the heat pipe not only acts as a separating wall but also facilitates the transfer of heat by condensation, evaporation and condensation of the working fluid inside the heat pipe. In general, if the fluids are immiscible, the separating wall may be eliminated and the interface between the fluid replaces a heat transfer surface as in the direct contact heat exchanger. Seeing different types of heat exchanger, a heat exchanger consists of heat transfer elements such as a core or matrix containing the heat transfer surface and the fluid distribution elements such as headers, manifolds, tanks, inlets and outlet nozzles or pipes or seals. The heat transfer surface is a surface of the exchanger core that is in direct contact with the fluids and through which heat is transferred by conduction. That portion of the surface that is in direct contact with both the hot and the cold fluids and transfers heat between them is referred to as primary or direct surface. To increase the heat transfer area, appendages may be intimately connected to the primary surface to provide an extended secondary or indirect surface. These extended surface elements are referred to as fins. Thus, heat is conducted through the fin and convected from the fin through the surface area to the surrounding fluid or vice versa. Depending on whether the fin is being cooled or heated, as a result, the addition of fins to the primary surface reduces the thermal resistance on that side and thereby increases the total heat transfer from the surface for the same temperature difference. There are multiple types of heat exchangers available depending upon their application in various parts of the industry. Seeing the first one, that is the shell and tubes heat exchangers. To make it simple, this type of heat exchanger works with a series of tubes containing the fluid that must be either heated and cooled, and these tubes run in the shell or much larger tube containing another liquid that either heats up and warms the tube or absorbs and cools the fluid running in the smaller tubes. Shell and tube heat exchangers work better in high pressure and demanding environments. Second heat exchanger is the plate heat exchanger, in which it works with a lineup of multiple thin and closely placed plates. The second heat exchanger is the plate one, with a lineup of multiple thin and closely placed plates which have a very large surface area and a fluid flow passages for better heat dispersion. Plate heat exchangers are more practical compared to shell and tube one in applications where there is a space restriction. The third one is adiabatic wheel heat exchanger. These type of exchangers uses a separate material which can either be a solid or a liquid material to store the held heat, which then moves to another side of heat exchanger to be released. The fourth one is the plate fin heat exchanger, in which usually made of aluminium alloys with varied designs such as cross flow, counter flow, along with different type of fins, which result in very effective heat transfer. They, however, offer a disadvantage at times in the procedures of servicing them correctly because of the extreme thin plates. Seeing the different classifications of the heat exchangers according to the construction features, they are frequently characterized by construction features. Four major construction types are tubular, plate type extended surface, and regenerative exchangers. Heat exchangers with other constructions are also available, such as crabbed surface exchanger, tank heaters, cooler cartridge exchanger, and other. Some of these may be classified as tubular exchangers, but they have some unique features compared to conventional tubular exchangers. It may be classified as tubular heat exchangers, plate type, regenerative, and extended surface. Seeing in detail the tubular heat exchangers, they are generally built of circular tubes, although elliptical, rectangular, or round, flat, twisted tubes have also been used in some applications. There are considerable flexibility in the design because the core geometry can be varied easily by changing the diameter, the length, and the arrangement. Tubular exchangers can be designed for high pressures relative to the environment and high pressure differences between the fluids. Tubular exchangers are used primarily for fluid to liquid and liquid to phase changes, condensing or evaporation. Heat transfer applications. They are used for the gas to liquid and gas to gas heat transfer application primarily when the operating temperature and pressure is very high or fouling is a severe problem on at least one fluid side and no other type of exchangers would work. These exchangers may be classified as shell and tube, double pipe, and spiral tube exchangers. They are all prime surface exchangers except for exchangers having fins outside and inside the tube, which is shown in the figure. Seeing the shell and tube exchangers, this exchanger is generally built of a bundle of round tubes mounted in a cylindrical shell with the tube axis parallel to the shell. One fluid flows inside the tubes, the other flows across and along the tubes. The major component of this exchanger are tubes or the tube bundle, shell, front end head, rear end head, baffles, and the tube sheets. A variety of different internal constructions are used in the shell and tube exchangers depending on the desired heat transfer and pressure drop performance and the method employed to reduce thermal stresses to prevent leakage. To provide for ease of cleaning, to contain operating pressures and temperatures, to control corrosion, and to accommodate highly asymmetric flows. Shell and tube heat exchangers contain a large number of tubes, sometimes several hundred, packed in a shell with their axis parallel to that of the shell. Baffles are commonly placed in the shell to force the shell side fluid to flow across the shell to enhance the heat transfer and maintain uniform spacing between the tubes. The three most common types of shell and tube exchangers are fixed tube sheet design, U-tube design, and floating head type. In all the three types, the front end head is stationary while the rear end head can be either stationary or floating depending on the thermal stresses in the shell tube or tube sheet due to temperature differences as a result of heat transfer. Figure 1 clearly shows the tubular heater. Tubular exchangers are custom designed for virtually any capacity and operating conditions, such as from high vacuum to ultra high pressure over 100 megapascals, that is 15,000 psig, from the cryogenics to high temperature, and any temperature and pressure difference between the fluids limited only by the materials of construction. They can be designed for the special operating conditions, vibrations, heavy fouling, heavy viscous fluids, erosion, corrosion, toxicity, radioactivity, multi-component mixtures, and so on. They are the most versatile exchangers made from a variety of metals and non-metals materials. Figure 2, additional tube configuration is shown, which is used in the shell and the tube exchangers. Seeing the double pipe heat exchanger, this type of exchanger usually consists of two concentric pipes with the inner pipe plane or finned as it is shown in the figure. One fluid flows in the inner pipe and the other fluid flows in the outer pipe in a counterflow direction. For an ideal highest performance is given as the surface area is high. However, if the application required an almost constant wall temperature, the fluids may flow in a parallel direction also. This is perhaps the simplest heat exchanger. Flow distribution is no problem and cleaning is done very easily by disassembly. This configuration is also suitable where one or both of the fluid is at very high pressure, because containment in the small diameter pipe or tubing is less costly than containment in the large diameter shell. Double pipe exchangers are generally used for small capacity applications where the total heat transfer surface area required is only 50 meters square or less, because it is expensive on the cost per unit surface area. Stacks of double pipe or multi-tube heat exchangers are also used in some process applications with radial or longitudinal fins. The exchanger with a bundle of U-tubes in a pipe or a shell of 150 mm diameter and above uses segmental baffles and is referred to variously as a hairpin or jagged U-tube exchanger. This is shown in the figure. Moving towards the next type of heat exchanger, which is the spiral tubes. They consist of one or more spirally wound coils fitted in a shell. Heat transfer rate associated with the spiral tube is higher than that for a straight tube. In addition, a considerable amount of surface can be accommodated in a given space by spiraling. Thermal expansion is not a problem, but cleaning is almost impossible. Seeing the inductive heating, all metals offer some resistance while conducting the electricity. The resistance to the flow of current causes power loss that show up in the form of heat. This is because, according to the law of conservation of energy, energy is transferred from one form to another and it is not lost. The losses produced by resistance are based upon the basic electrical formula, that is P is equal to I square R, where I is the amount of current and R is the resistance. Because the amount of loss is proportional to the square of the current, doubling the current significantly increases the loss or heat produced. Some metals such as silver and copper have very low resistance and consequently are very good conductors. Metals such as steel have high resistance to an electric current, so that when an electric current is passed through the steel, substantial heat is produced. Inductive heating is based on the supply of energy by means of electromagnetic induction. Induction heating is a fast, efficient, precise, repeatable and non-contact method for heating metals or other electrically conductive materials. A coil suitably dimensioned placed close to the metal part to be heated, conducting high or medium frequency alternating current induces on the workpiece currents, that is the eddy currents, whose intensity can be controlled and modulated, is used. Induction heaters are used to provide alternating electric current to an electric coil that is termed as induction coil. The induction coil becomes the electrical source that induces an electrical current into the metal part to be heated, called the workpiece. The work coil, also known as inductor, is the component in the induction heating system that defines how effective and how efficiently the workpiece is heated. The work coil range in complexity from a simple helical wound coil consisting of number of turns of copper tube wound around a mandrel to a coil precision machined from solid copper and brazed together. No contact is required between the workpiece and the induction coil, as the heat source and the heat is restricted to localized areas or surface zone immediately adjacent to the coil. This is because the alternating current, that is AC current, is an induction coil has an invisible force field that may be electromagnetic or flux around it. When the induction coil is placed next to or around a workpiece, the lines of force concentrate in the air gap between the coil and the workpiece. The induction coil actually functions as a transformer primarily with the workpiece to be heated, becoming the transformer secondary. The force field surrounding the induction coil induces an equal and opposing electric current in a workpiece, with the workpiece then heating due to the resistance to the flow of this induced electrical current. The rate of heating of the workpiece is dependent on the frequency of the induced current, the intensity of the induced current, the specific heat of the material, and the magnetic permeability of the material with the resistance of the material to the flow of current. The induced currents are sometimes referred to as eddy currents, with the highest intensity current being produced within the area of the intense magnetic fields. Induction heat treating involves heating a workpiece from room temperature to a higher temperature, such as is required for induction, tempering or induction austenization. The rates and the efficiencies of heating depend upon physical properties of the workpiece as they are being heated. These properties are temperature dependent and heat specific. Magnetic permeability and resistivity of materials changes with the temperature. The depth of penetration of the generated currents is directly correlated to the working and frequency of the generator used. Higher is it, much more the induced currents concentrate on the surface. In this case, the heating homogeneity on the relevant mass can be obtained due to the principle of thermal conduction, which allows the heating to be transferred in depth. The material of workpiece may be a metal such as steel, copper, aluminium or braces, or it can be a semiconductor such as carbon, graphite or silicon carbide. To heat non-conductive material such as plastic or glass, induction can heat an electrically conductive suspector, typically graphite, which then transfers the heat to a non-conducting material. Induction heating is used in the processes where temperature are as low as 100 degrees Celsius and as high as 3000 degrees Celsius. Induction heating is used in domestic and commercial cooking and in many applications such as melting, heat treating, preheating, welding, brazing, soldering, curing, sealing, shrink fitting in industry and in research and development. Basis of induction. The phenomena of the electromagnetic induction is therefore based on the three physical principles. They are explained as: first one, transfer of energy from the inductor to the piece to be heated by means of electromagnetic fields, transformation of the electric energy into the heat due to Joule's effect, that is P is equal to I square R. The third one is transmission of the heat inside the mass by the means of thermal conduction. Induction creates an electromagnetic field in the coil to transfer energy to the workpiece to be heated. When an electric current passes along a wire, magnetic field is created around that wire. When the electric current changes the direction, the magnetic field created collapses and is created in the reverse direction as the current reverses the direction. When a second wire is placed in that alternating magnetic field, an alternating current is generated in the second wire. The current in the second wire is proportional to the current in the first wire and to the inverse of the square of the distance between them. When we replace the wire in the model with a coil, the alternating current on the coil creates an electromagnetic field while the workpiece to be heated is in the field. The workpiece corresponds to the second wire and an alternating current is generated in the workpiece. Heat is generated in the workpiece due to the I square R losses of the workpiece material resistivity. This is called eddy's current heating. Seeing the working of the induction coil. The induction coil is used to transfer energy to the workpiece using an alternating electromagnetic field. The alternating current flowing through the coil generates the electromagnetic field, which induces a current flowing in the workpiece as a mirror image to the current flowing in the work coil. The work coil, also known as inductor, is the component in the induction heating system that defines how effectively and how efficiently the workpiece is heated. Work coil range is complexity from a simple helical wound or solenoid consisting of a number of turns of copper tube wound around a mandrel to a coil precision machined from solid copper and braced together. This can be easily seen in the figure. An induction heating system consists of a power supply, a tank circuit, and a work coil. In industrial application, there is usually enough current flowing through the coil to require water cooling, so a typical installation includes a water cooling system. The power supply converts the alternating current from the AC line to an alternating current that resonates with the combination of the capacitance in the workhead, the inductance of the coil, and the resistivity of the part. Looking towards the what is skin effect is, the basic nature of induction heating is that the eddy currents are produced on the outside of the workpiece in what is often referred to as skin effect heating because almost all of the heat is produced at the surface. The eddy currents flowing in the cylindrical workpiece will be most intense at the outer surface, while the currents at the center are negligible. The depth of the heating depends on the frequency of the AC field, the electrical resistivity, and the relative magnetic permeability of the workpiece. The skin heating effect is defined as the depth at which approximately 86% of the heating due to resistance of the current flow occurs. The reference depth decreases with higher frequency and increases with higher temperature. Now we will conclude the lecture. Heat exchangers or interchangers are devices that facilitate the exchange of heat between two fluids that are different temperatures while keeping them away from mixing with each other. Heat exchanger differ from mixing chambers in that they do not allow the two fluids involved to mix. There are multiple types of heat exchangers available depending upon their application in various parts of the industry. Heat exchangers are frequently characterized by construction features. Four major construction types are tubular, plate type, extended surfaces, and regenerative exchangers. Tubular heaters are generally built of circular tubes, although elliptical, rectangular or round flat twisted tubes have also been used in some applications. All metals offer some resistance while conducting electricity. The resistance to this flow of current causing power loss that show up in the form of heat. Inductive heating is based on the supply of energy by means of electromagnetic induction. Hope you all enjoyed this informative lecture. Thanks for the attention. Keep studying and goodbye. Question number 1. What is inductive heating? And the answer is, inductive heating is based on the supply of energy by means of electromagnetic induction. Induction heating is a fast, efficient, precise, repeatable, non-contact method for heating metals or other electrically conductive materials. Induction heaters are used to provide alternating electric current to an electric coil. The induction coil becomes the electrical source that induces an electric current into the metal part to be heated called the workpiece. Question number 2. What are heat interchangers? And the answer is, heat exchangers or interchangers are devices that facilitates the exchange of heat between two fluids that are at different temperatures while keeping them away from mixing each other. A heat exchanger is a device that is used to transfer thermal energy between two or more fluids, between a solid surface and a fluid, or between a solid, particulates and a fluid at different temperatures and in thermal contact. In heat exchangers, there are usually two external heat and work interactions. Heat exchangers are commonly used in practice in a wide range of applications, from heating and air conditioning systems in the household to chemical processing and power production in large plants. They differ from mixing chambers in that they do not allow the two fluids involved to mix.